First of all, I would remind you of one particular nice set of Westerns that we have in the movies called spaghetti Westerns. Maybe you know, in particular, director Sergio Leone was very, produced lots of films on this, and there was a particularity in his films. There were no good guys. So everybody were bandits. So, I decided to call hydrogen the Sergio Leone element because it seems that every place that you put hydrogen, it brings something bad for us. But just to remind what we know about hydrogen and materials. First of all, it's not a new problem, so it's already identified some 150 years. Of course, we know it brings a decrease in strength, so it leads to delayed fracture, which is even worse in service because you produce a component and suddenly it breaks, so it's not very funny to have this kind of problem. It's particularly severe in high-strength steels. So the own steels that we use for good purpose are the most suitable to present hydrogen and Brittleman. And of course, when something is that bad, it is unlikely it is bad just for one cause. So there are multiple damage mechanisms in many materials, and there are interactions between the mechanism. This is nice. It's okay. And of course, we find hydrogen everywhere. So everywhere we have hydrogen. So we cannot live without. We cannot live without. So there is a worldwide movement in using hydrogen. And now is the time in which we really have to investigate hydrogen and Brittleman. Because as everybody knows here, we watched many presentations here already in this section. So we have to transport hydrogen. We have to produce hydrogen. We have to store hydrogen. So we have to know what hydrogen is doing. So this is our time. This is the time that we will be called to give answers to the technology. And of course, the reason is this here. So we are not only working in one of the critical problems of mankind. We are working in two. So producing energy in a clean way and controlling climate change. So this is what we are doing here. And of course, this I picked it up from Milos' seminal work. This is just to show how complex the problem is. So we have so many things to take care when we are talking about hydrogen and Brittleman that it's no wonder that we are working 150 years in the problem and we still don't have a solution. So okay, it's this gives us money to research. And this I took from Mateo's work, but of course it's not from him. And the problem is that we have problems, still have problems here to detect hydrogen, to observe hydrogen in action. This is a reason to investigate all these things. Then talking to my colleague in the Federal University of Rio Grande do Sul, which is very far in the south of Brazil, he reminded old work he published many years ago. he investigated cracks in silicon due to hydrogen. In that case, he had to implant hydrogen to produce the crack, but he had also to implant helium to produce this residual stress to cause the cracking. And he suggested we should do the same in our steel. What we are doing, we are working with 22 manganese boron 5 steel, is that press hardening steel, which is used for the safety network in cars. It has, sadly, a martensite microstructure, and sadly because you know how messy martensite is for TEM observation. In particular because it's ferromagnetic too. It's full of dislocations, full of defects, and ferromagnetic. Everything that is hard to look in TEM. We produce 3mm discs for use in the TEM, reducing the thickness to 100 microns, polishing in alumina, and to protect from oxidation, we stored in gel caps. The original idea was to do two kinds of samples. The first one was what we call the face-on sample. We would implant hydrogen and then approach both sides, one with the dimpler, the second one with IO milling, so that we could observe the region affected with hydrogen. The other idea was to implant hydrogen in different depths with different quantities and then produce a feed sample to look at very different hydrogen levels. This is the first experiment we did, and I must say to you that we are in the beginning in this area. So we had only the first experiments to report. And we did a simulation, and this produces a hydrogen layer some 150 nanometers below the surface. So it's not very nice. This, please don't pay too much attention to this because this is quick and dirty. We prepared a sample with twin jet polisher just to see if we could look at the microstructure. And so there are full of artifacts and other things. So we still are securing time in the feed to do the experiment. But anyway, I can see here some changes. This is the usual left microstructure of the martensite. And I imagine there are some changes here in the region affected by hydrogen. One problem that was already identified is that EO implantation produces irradiation damage, and this could produce defects, and we have to separate this. One of the first solution was to implant something else than hydrogen with the same damage level so that we could identify what is the irradiation damage. But then I reminded something. Imagine that we have an implanted hydrogen layer. So the ions arrive from this side. The damage occurs in the front side of the sample. Hydrogen stops here because it doesn't have energy enough to go further. So the rear side is not damaged, but hydrogen diffuses. So then the next plan is to prepare a feed sample with the implanted hydrogen some months after implantation, so that we can have sufficient diffusion in the other area, and then observe here in the non-damaged area. So this is what we are trying to do, and we think it's sufficient, so we can introduce a localized hydrogen amount below surface. There are problems because we are dealing with ferromagnetic martensite. We believe that the damage can be separated from the ion damage can be separated from the hydrogen damage. And we believe that our results can find cracks in the nucleation range in this martensite. This is what we are trying to do. The important thing is that martensite, with all its problems, has one thing that is very good. It's full of residual stresses. So we believe we will find the cracks in the eye. That's